Maths educational video, Introduction to Line Integrals. In this video, we are going to talk about the concept of integrating a function over a curve. As a motivation, let's recall something we already know. And that is integration of a function over an interval or a straight line joining 2 points A and B on the x-axis. We all know that this integral represents area under the graph. But the reason why it represents area is because of the so-called Riemann sum theory that we will briefly explain. A complete mathematical treatment of this Riemann sum theory is beyond the scope of this course. Roughly speaking, the Riemann sum theory says this. When finding the area under the graph, we will first form a rectangle covering part of the area. The rectangle has a base delta t. Delta t is some small number. And as x equals to t, the height of the rectangle will be given by f of t. So as a result, the area of this rectangle is base times height, which is delta t multiplied by f of t. And we are going to cover this entire shaded region with such rectangles. From x equals to a to x equals to b. We're going to sum the areas of these rectangles and then we let delta t go to 0. That limit will be equal to our integral. So we skip the mathematical details, but that's the idea behind the Riemann sum theory. An integral is actually the sum of the rectangles covering the shaded region and then with delta t going to 0. So you can imagine there will be infinitely many such rectangles as delta t becomes smaller. We would like to apply this concept to what we are going to do now. And that is to integrate a function of two unknowns, say f of xy, over a curve on the xy plane. And according to the Riemann theory, we have to form rectangles. But first, a quick remark. The function fxy, as you know, has a graph which is a surface in the three-dimensional space. But since we are integrating the function along the curve, the red curve, the domain becomes this red curve. So we only consider the part of the surface, which is the green curve, that corresponds to the red curve. So any point on the green curve will be given by these coordinates, xt, yt, and f of xt, yt. I just mentioned earlier that in order to define the integral of f over the curve c, we have to form rectangles. So that will be done in a similar fashion. We take two neighboring points on the red curve and we form a rectangle. As you can see, it's not exactly a rectangle, but because delta t is going to be small, it will be approximately a rectangle. And as before, the height of this rectangle will be given by the value of the function f at this point t. So it will be f of xt, yt. The width is the length of this part of the curve, the part in green. We call it delta s. So the area will be f of xt, yt multiplied by delta s. But delta s actually turns out to be this expression. We skip the mathematical proof here. What's important is this. According to the Riemann theory, we are going to add up all such areas and we will let delta t go to 0. So essentially, we'll be integrating something like this. We'll be integrating this expression that we saw earlier. And hence, the formula for the so-called line integral is given in the box. So here's a summary, and also a notation for line integral is given here in red. You write integral of f ds with c, the curve, as a subscript to the integral. There's an interesting special case. When the function f is identically equal to 1, that means it's a constant function, we end up getting the arc length of the curve. And naturally, we can extend the line integral to the case when the curve is a three-dimensional curve and the function is a function of three unknowns. And as before, the special case fx yz equals to 1 gives us the arc length of the curve C. Finally, we talk about integrating function f over a union of curves. As we know, integrals are linear, so we expect the integration of f over a union of curves to be the sum of the individual line integrals.